Good morning, friends. I am Dr. DN Pansare, Assistant Professor, Department of Chemistry, Devi College, Aurangabad. Today we discuss about the stereochemistry. Stereochemistry, it is the interesting part in the organic chemistry. Regarding, we will see the stereochemistry of the organic compounds. So let us discuss about the stereochemistry. Okay. Stereoisomers can be easily classified on the basis of mirror images relationship. Stereoisomers with non-superimposable mirror image relationships are enantiomers. These relationships required for the enantiomers can be checked by actually fitting molecules model on each other by summary or symmetry operations. Mirror image of either an asymmetric molecule or a dissymmetric molecule is always non-superimposable on its original molecules. Nevertheless, the minimum requirement for the observation of the chirality in the molecules is not symmetry, but it is a dissymmetry or molecule possess only C2 axis as the element of the symmetry is the dissymmetric molecules. This is the examples of the organic compounds. This is the S hexane to all, and this is R hexane to all. That is, substitution pattern or substitution of the functional groups is attached to the carbon chains on the above the plane and below the plane of the different types of groups. Depends R and S conformations. These are homomers and stereomers. The below examples also is different. In the one of the group is OH group is above and hydrogen is below. Symmetric molecules have their mirror images superimposable on the original form because this image actually put on this image, it is exactly matched, then we call these are superimposable on its mirror images. This is another examples. These are hexane triol. Both hydrogen and OH group is above the plane. Second structure, it is below the plane. And again, if it is flipped at 180 degree, then it's come at the right hand side. OH group is above and hydrogen is below. Again, yes, hexanol, it's again a rotate 180 degrees Celsius. Then this OH group is exactly vice versa to this product. In the reactant, OH group is on the below side. If we flip 180 degree, then hydrogen is come on the above sides. Again, this flip like this manner. Again, OH and hydrogen is below the plane. The property of the non-superimposable of molecule on its mirror image is chirality. The elements of the chirality are chiral centers, chiral axis, chiral plane, helicity. It can be checked by local symmetry. Dissymmetry is synonyms for chirality. It is a geometric properties of the whole molecules. It does not reside on any of the atom in the molecule. Atom residing in a chiral environment are chirotopic. Chirality is required for the occurrence of the enantiomerism. A tetrahedral atom attached to 4 different ligands is said to be chirogenic atom or center. That is the chiral center. Again, we can see this is the 1,2-dimethyl cyclopropane. In this group, This is the C2 axis, it's rotate. Again, these methyl and hydrogen group as it is. If it flip 180 degrees Celsius, then exactly these are the mirror images. Then we call R converted into the S, that is 1S, 2S, 1,2-dimethyl cyclopropane. Again, second example, 2R, 3R, butane, 2,3-diol. Again, it is C2 axis of symmetry. It is rotate at C2 axis. Means it turns into 2s, 3s butane, 2,3-diol. These two molecules exactly mirror images of the each other. Now, this example 2R, 3R, 2,3,4 trihydroxybutanol. These are also, this carbon is R, this carbon is also R. In this structure, this OH group is thrioform, means exactly opposite to each other. That's why the enantiomers or stereoisomers is 2R, 3S, 2,3,4 trihydroxybutanol. Again, same example. Here also 2S, 3S, 2,3,4 trihydrobutanol. Means the rotation is depends on the OH group is attached at the left side or right side. Then first give the priority to the highest molecular weight or atomic number molecule. Then give priority 1, 2, 3 and rotate this molecule clockwise or anti-clockwise. If clockwise rotation takes place, then R conformation. If rotation is anti-clockwise, then the conformation is S conformation. Enantiomers exist in pairs. They have opposite configurations at each and every chirogenic center. They are isometric as all the interatomic distance and internuclear distance are identical. They show different behavior with chiral agents. Plain polarized light is a chiral, hence enantiomers differ only in direction of the optical rotation, but not in the magnitudes. Stereoisomers with no mirror image or relationships are diastereomers. More than one chirogenic center are required for the occurrence of diastereomerism, at least two. Diastereomers may be more than two in the numbers. They are anisommetric. They have as if they were different compounds. Stereoisomers are also classified on the energy based requirement for the interchange of one into another. Configurational isomers have high energy barrier for their interconvergence, that is more than 100 kilojoule per mole. Conformation isomers require less energy for their interconversion, that is less than 60 kilojoule per mole energy. Configurational isomers are subdivided into configurational enantiomers and configurational diastereomers. Conformational isomers are also subdivided into conformational enantiomers and conformational diastereomers. Now, energy-based classification of the stereoisomers, configurational enantiomers, and diastereomers. These are 2R, 3R butane, 1, 2, 3, 4 tetraol, that is 4 alcoholic group. These are 2S, 3S butane, 1, 2, 3, 4 tetraol, that is This configuration is depends on OH group. It's situated at the left side or right sides. Conformation in enantiomers and diastereomers. These are the eclipse and staggered conformation. These are molecules is Newman projection formula situated as staggered. Also, this methyl group is anti to each other. Again, rotate at 120 degrees Celsius. Then these two methyl groups are near to each other around 60 degrees. Again, this methyl group rotate at 120 degree. Then it's become at left side. Conformational enantiomers and diastereomers. This is the change conformation and methyl group is axial. If axial methyl group is present at chain conformation, then it's unstable because it is higher energy. Again, it flip at 180 degree. Then these axial methyl groups come at equatorial position, and equatorial position methyl group is energy is less. If two methyl groups is attached at the chain conformation, one is axial and one is equatorial. If this group is flipped, then this equatorial axial group become equatorial and equatorial group become axial at the position. Again, we can see same phenomena here. One is axial, one is equatorial. Carbonic atom is a tetrahedral atom attached to the different ligands. Number of stereoisomers in a compound can be decided by the number of the carbonic centers present in it. For asymmetrically substituted molecules, the number of stereoisomers is 2 raised to n. All of them will be optically active. There will be the enantiomer existing in a pair. One enantiomeric pair will be diastereomeric to such an order pairs. Stereogenic atom is one of at which exchange in the position of two ligands gives rise to a new stereoisomers. Hexane 2-ene, and this is a Z-hex 2-ene. Chirogenicity can be checked by the local symmetry. Stereogenicity can be decided by the disposition of the two ligand. All chirogenic atoms are always stereogenic. All stereogenic center may not be always chirogenic center. This is the stereogenicity compound. These are Newman projection formula. This acid, alcohol gives one number, here 2 and 3. And fourth number is choose horizontal. Then conformation is reverse. That's why it is an R configuration. Again, OH is below, hydrogen is above the sides. Again, these are the S2 hydroxypropanonic acid. Here, OH is left side and hydrogen is right side. They bear 1, 2, and 3. But for group at horizontal, that's why the reverse phenomenon. Yes, configurations. Okay, friends, thank you very much for your patience. I think you got the idea about the confirmation and its analysis.